Okay, so number 3 on the test gave me the most trouble. I think the hardest part in this question was part A, which was finding the gravitational acceleration for Mars. I had trouble figuring out what formula to use since it didn't give me a mass for Dr. Greco. But after messing around for a little bit and realizing that the formula, no matter what, is G times M1 times M2 over R squared, you figure out that instead of having two different masses, you're supposed to use just the mass of Mars for both of the masses. So it's just the mass of Mars squared. You do this because it doesn't give you the mass of Dr. Greco. So for the force of gravity, you use the formula gravitational constant times mass of Mars squared over the radius of Mars squared. And you use the radius of Mars squared because that's the magnitude of distance between the surface of Mars and the center of Mars. So using that, you can find the gravitational force. And remember that force is equal to mass times acceleration. So you have F equals ma, and you can find the acceleration by dividing the force by the mass, which will just single out acceleration. So using that, you can find that the gravitational force is 8.07 e to 10 times 10 to the 30. The gravitational force equals 8.07 times 10 to the 30th power. And you can find that acceleration equals 3.725 meters per second squared. The next part, which is a little bit complicated since it's springs, you find that, well, you use the formula spring force equals negative Ks times the unit vector of L. And since the spring straight up and down, the unit vector is 0, 1, 0. And you can find, it gives you the K constant, and then you find the S value by subtracting 0.2 meters by 0.28 meters, so you get negative 0.08 meters. Using that, you can find the force. You can also find the gravitational force in part B by multiplying the gravitational acceleration found in part A, 3.725 meters per second squared, by the mass of the block in part B, which is negative 3.725 times 0.06, and you can get your answer for force of gravity right there. And so you need to find the F net to figure out like how the spring's going to be moving. So you find F net by adding together the spring force and the gravitational force, and you just add these two different vectors together, and then you find your answer, which is 0, 0.4725, 0 newtons. Then for part C, which is the cluster of terribleness, use the net force, and then you can use, well, you use the momentum principle, and you have the net force, and it gives you the change in time, and it wants you to split into two intervals. Each one is 0.1 seconds. So you do the first interval, use the momentum principle. You have, change in p equals f net times delta t. Delta t is 0.1 seconds. So you use some algebra right there. You put in your f net, you put in the delta t, and you also can reason that the initial momentum is 0 because it's not moving at all. It doesn't have like an initial velocity, so it's 0. So you can find the final momentum, and using that you can divide the final momentum by the block's mass, and you can use that to find the velocity. Use that to find the final position. For the final position, you have final position equals initial position plus velocity times change in time. So you find the first final position, you find the first momentum, and then you find the new spring force, because it's in the second interval it's moved some, because in the first interval it gained a velocity. So you find the new spring force. You use the movement of the block to find the new position, which is where our final was in part 1. You figure out the change from the equilibrium position that was back in part B. So you figure out the new spring force, which is equal to Ks times the unit vector. Anyway, so you figure that out, you get 0,0101875, 0 newtons for the spring force. The gravitational force is still the same, so you find the new F net, which is 0, negative 0.212, 0 newtons. And then using this in the momentum principle, you once again find the final momentum, and then you use this final momentum again to find the final velocity, and thus its final position at the end of this 0.1 second time interval. Thank you. Boop, 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 boop.